I'm Geethika, and with my group today we are going to prove if one of the clips in the Phineas and Ferb episode can happen in real life or not. Which clip, you might ask? Let me just show you.
Terry the Platypus, right? Well, I did not see that coming. Calling headquarters, huh?
Looking at this video, what do we need to find? We need to see how much Perry needs to pull to drag Dr. Doofenshmirtz across the floor and how much an actual platypus can pull. Do you think this is possible? Let's find out.
Oh my god, look, someone wrote down our find, so let's write down the steps.
Oh my god, look, free body diagram. So we have the force of wood on Doofenshmirtz, force of gravity on Doofenshmirtz, which cancel out, force of friction on Doofenshmirtz, and force of Perry on Doofenshmirtz at 5 degrees. So what else do we need to find? We need to find the neutral force, coefficient of friction, then acceleration, of course. Then to finally find force of Perry on Doofenshmirtz to see if this scenario can actually happen in real life.
Dr. Doofenshmirtz is a 47-year-old male and he's 6'3". Knowing this, we can find out his weight is 207 pounds or 93.9 kilograms, based on the height and weight for a 47-year-old male. The average platypus weighs 1.8 kilograms, and that's the weight we use for Perry the platypus. For the time, we said it was 5 seconds because Dr. Doofenshmirtz is being dragged from where he starts to the pole where he ends up for 5 seconds, as shown in the clip. And then we measure the distance he traveled to be 4 meters using cutouts and his torso length. Figured out his torso length because of scaled down proportions. We used these cutouts here. So in this picture, we see that he's getting kicked, and then he ends up right at the start of that second window. Using this cutout, his torso length is right there, right? And that's one torso length, so that's 1.27 meters right there. And we see his head's right at the start of that second window there. So we can go over to the other picture and see that if that's one torso length, we can move him one more time. Okay. And then that's 2 torso lengths right at the end of the window right there. And we can move it one more time to be 3 torso. Okay, sorry. 3 torso lengths. And we see he's not quite there, but about half of his torso more. And he ends up right there. So that's how we got 4 meters for that. We said his starting position was 0, and that he ended up at 4 meters, so the initial velocity is 0. And he's wearing a lab coat and being dragged on wood, so the coefficient of kinetic friction of lab coat versus wood is 0.9. We found the angle that Dr. Doofenshmirtz was being dragged at because when we played the clip, we took the angle he was being dragged at and we used a protractor, and that ended up being 5 degrees. And we figured out by searching it up that a platypus can pull a maximum of 300 newtons.
Are you ready to do some math? Let's do it. So first, we're going to find the neutral force. We're going to do that by using the F net y equation, which is F net y is MAY, which is equal to force of Perry on Doofenshmirtz on the y, plus force of the wood on Doofenshmirtz on the y, plus gravity on Doofenshmirtz. We can plug in the knowns. Simplify that out. Instead of mg, we have 93.9 times negative 9.8. And then we simplify that out to get force of the wood on Doofenshmirtz minus 894. Move that to the other side. And then we have proper sig figs. 890 is equal to force of the wood on Doofenshmirtz. Now we're going to find the force of friction on Doofenshmirtz using the coefficient of friction equation. This is the equation. Coefficient of friction is the neutral force times the frictional force. Plug in the knowns and simplify it out to get force of friction on Doofenshmirtz is 988 newtons or 990 newtons with proper sig figs. Next, we're going to find acceleration in the x direction. We're going to use the x naught, a v naught, and v, an acceleration, and a t. We have all of the knowns that we got in the previous section. Then we're going to plug that into the kinematic equation. We're going to plug in the knowns that we have, simplify it out, and we get 14.5a, and then 3.125a, which is going to be equal to 3.1 meters per second squared. Next, finally, we're going to find the force of Perry on Doofenshmirtz in the x direction. We're going to use the F net x equations, and that's going to be equal to force of Perry on Doofenshmirtz on the x plus the force of friction on Doofenshmirtz. We're going to plug in the knowns. Remember, we got this from the previous section with the coefficient of friction. We're going to simplify that out, and even if we correct it to proper sig figs, they are not equal. And we'll explain why later.
Could this happen? No, because the mass times acceleration, which is 290, equal to the force of Perry on Dr. Doofenshmirtz, plus the force of friction on Dr. Doofenshmirtz, which is added up to negative 660, are not equal to each other. Thank you for listening.